We are very, very happy to welcome Dr. Jelena Diakonikolas, Assistant Professor at the Department of Computer Science at the University of Wisconsin at Madison, which is very beautiful this time of year. Before, she's worked as a postdoc at UC Berkeley and Boston University after receiving her PhD at Columbia. So Dr. Diakonikolas has done a lot of important work, in my opinion, on optimization for large-scale problems. And lately, she's also doing some work that we care a lot about in the area of MinMax optimization. She will summarize work from 3 publications, as far as I understand it. So without further ado, welcome, Jelena. We are all ears.
Thank you, Yanni. Hi, everyone, and thank you for joining this talk. I wanted to talk about some recent results in MinMax optimization. The title of the talk is Structured MinMax Optimization, and I'm taking this structure very broadly, as you'll see. But I wanted to share with you a few things that I find kind of surprising and curious, and then maybe a few ideas from the different papers that I don't know, you might or might not care about. So the setup for this talk is, as the title suggests, MinMax optimization. We have a function f of 2 arguments that we want to minimize over x and maximize over y. Typically, we will take the feasible sets for x and y to be closed and convex. This is sometimes possible to relax, but generally makes things quite complicated. So for this talk, and in general for my work at least, I only care about closed convex sets. We will sometimes, and actually for the majority of this talk, be assuming that f is convex concave, which means it is convex in x when we fixed y, and concave in y when we fix x. Now, one of the central results about MinMax optimization is a classical result due to von Neumann, known as the MinMax theorem, that tells us that when we have a function that is convex concave and feasible sets that are convex and compact, then we are guaranteed that a MinMax point exists, and we can exchange the order of min and max. And this is considered the central result in game theory. Von Neumann himself said that game theory wouldn't make sense if it weren't for this result. And also it is central in optimization. I guess probably everyone on the call has some background in optimization. This is heavily used in duality theory. When the function is not convex concave, then this MinMax theorem does not hold. And actually all of the assumptions in the MinMax theorem are important. But when we do not have a convex concave function, we cannot in general exchange the order of min and max, and even a local min-max point may not even exist. And there is a whole research area even just dedicated to figuring out when we can guarantee existence. And in many cases we care about this standard convex concave setup, but in many cases we also care about non-convex, non-concave setup. And since I guess most people here do applications in machine learning, we know that the problems such as this one will come up in adversarial training of deep neural net. They will come up in the training of generative adversarial networks, and so on.
We already have a question by Gauthier. Go ahead.
Hey, Jelena, I have an annoying question. I know it's annoying because I got this question asked to me many times, and I always have a hard time to justify it. Why is it so important to have min-max equals to max-min?
It is not always so important. If you're using duality, then obviously you do want to have min-max equal to max-min. More generally, in game theory, I guess you wouldn't necessarily. I'm not sure if defining equilibrium would really be very meaningful. but I'm not a game theorist, so that's probably a better question for them. There are probably setups when we don't care. And I know that a few people, especially with the machine learning background, have tried to justify that sometimes even just doing things sequentially and having a point that is locally optimal under the sequential order may make sense.
Okay, thanks.
Yeah, no problem. Okay, so there are two standard guarantees that we may require if we have some candidate approximate solution, and we always, do things with some target error epsilon. One is to have a small optimality gap, and this is generally something that we can get when F is convex concave, and it's your standard thing. You see how much you can improve over the max part plus how much you can improve over the min part, and the total should not be larger than epsilon. The second type of guarantee would be stationarity, which tells you that locally over some wall you cannot improve by more than epsilon. This may look like a complicated thing. It's just a generalization of stationarity you have for standard or min optimization. And if you're in the unconstrained regime, it just boils down to having a small norm of the gradient. Now, a few things I find really curious about min-max optimization, and many of you will be familiar with these, but I still think they're curious, is how different it is from standard min optimization. And if you're someone who is used to the standard min optimization, these things can look really similar. So the first thing you would be trying is to do something similar to min optimization, but some of the very basic things fail, right? Because let's just look at a couple of examples. So the first setup would be, in min optimization, you have a convex and smooth function that has a minimizer. For min-max, your counterpart setup would be to have a convex concave function that is all smooth and has a min-max point. For min optimization, this is a convex optimization setup. We know that if you take any candidate solution from RD, so here optimization is over RD, you have a finite optimality gap. Right? In min-max optimization, if you just relax compactness of your feasible sets, your optimality gap could be infinite. And there's a very simple example. You just take x times y, and I'll go through this example later in more detail. Second thing is your most obvious algorithm for min optimization, which is gradient descent, converges. It reduces the optimality gap, you know this. In min-max optimization, it diverges in general. The counterpart, which would be gradient descent ascent. If you go to the non-convex setups, things get even more interesting. So here, the setup for min optimization, you have a non-convex and smooth function, and let's say a minimizer exists, or let's say that the function is bounded below, whichever one you like. And for the min-max setup, you would have a non-convex, non-concave function that is all smooth. And let's assume a min-max point exists. For min optimization, if you run gradient descent, you know you're going to converge to a stationary point, which for unconstrained optimization is just a point with a small gradient, and you can get to a point with the gradient epsilon in poly 1 over epsilon time. For min-max optimization, finding an epsilon stationary point is PPAD complete. So this is a complexity class similar to, NP complete class in that all the problems within the class are polynomial time reducible to each other, and we do not know of any polynomial time algorithms for any of them. And here I'm talking just about making I'm talking about epsilon approximate point. I'm not talking about finding the exact min-max point. And you can say even more. If you look at Oracle-based algorithms, which are the algorithms you and I would probably try using here, then in fact exponentially many queries are required. Now this lower bound is for constraint setups. I will talk also a little bit more about this and make the statement a bit more concrete. But what I want you to just notice here, how different these two settings are and how much trickier min-max optimization can be.
We have a question from Simon.
Yes.
I guess on your previous slide. Go ahead, Simon.
Yes, it was just a quick clarification question on, so when you talk about a min-max point, you mean a saddle point where the min-max is equal to the max-min?
Yes.
Okay, because you could have, I mean, on compact set, you always have solution to the min-max problem. It's just now you're talking about very specific type of solution, right? Yeah,
so this result here is for compact sets, and they needed compactness to guarantee existence of a min-max point. And in that case, this result holds.
But again, so for you, a min-max point is a saddle point. It's not just the solution to the min-max problem.
It is a local min-max.
Okay, thanks. So local saddle point.
Yeah, so in this case, the way they would have defined it would be using, whoops, it would be using this notion of stationarity. And if you're familiar with the gradient mapping, it would be the same as saying the gradient mapping is less than or equal to epsilon. Does that make sense? So this was the notion of local min-max point.
But so you could have this tertiary condition satisfied and not be a real local min-max, right?
Yeah. Oh, actually, for the complexity result, you just need this condition. This is already applied.
Nice. Cool. Thanks.
Yeah.
And you're using the fact that for smooth problems, all locally min-max points are also stationary points, I guess, right? Okay. Okay, thank you.
Okay, so oops, I can just skip to this. Okay, so in the first part of the talk, and I'll actually spend probably most of the time on this, it will be the convex-concave setup, convex-concave smooth setup, where it doesn't make sense always to approximate the optimality gap, and I'll talk about approximating stationary points. I will briefly talk about the non-convex, non-concave setups and what can be done there, and just present like one result, and I'll probably spend not more than 5 minutes on this. And then I wanted to, like, just for good measure, add one more result, which is a convex optimization problem coming from empirical risk minimization, where actually taking a min-max perspective turns out to be quite useful. And by taking the min-max perspective, we get better results than we had before. So it's not always, that min-max optimization presents challenges. Sometimes it can be useful even when we know how to do things in a different way. Okay, so for all three results, you'll see a slide that looks like this. It has a QR code that would lead you to the paper and the citation of the paper that I'll talk about. So this setup is convex-concave, and very frequently, these problems are studied through further abstractions. And those abstractions use monotone operators. And I'll remind you what monotone operators are. So monotone operators are maps. In this particular case, I'll take from RD to RD, and for any 2 points, they satisfy something like this. So this holds for gradients of convex functions, but also for convex-concave functions. If you stack the gradient with respect to the convex part and the negative gradient with respect to the concave part, you end up with the monotone operator. And this is heavily used in the optimization literature. Now, the types of problems that are typically considered here, some of them are known as variational inequalities, and there are two standard ones known as Minty and Stepakia variational inequalities, and their solutions are known as weak solutions and strong solutions. They look quite similar. The difference is where this operator is evaluated. Let's not focus too much on that. I'll get to the bottom line very quickly. Another type of problem that can be considered is known as monotone inclusion. And here you're looking for 0 of the operator plus this weird thing here is the subdifferential of the indicator of your feasible set. So all it does, it just accounts for the cases when you have constrained optimization and your solution may be at the boundary of the feasible set. So if you were in the unconstrained regime, this would be the same as just looking for the 0 gradient. Okay, so you can think about this variational inequalities as minimizing the optimality gap, and monotone inclusion as finding a stationary point. Right? And if you look at all these different requirements, there is a basic fact that tells you that if you look at optimal solutions to any of these 3 problems, they're all the same. If your operator was a monotone, and here I'm considering that case. This is known as Memphis Theorem. But we can't really find optimal solutions in general, can we? Right? So normally we can only find approximate solutions, and you would define your approximate solutions in the standard way. You just add some epsilon margin, right? So for monotone inclusion, this is a ball of radius epsilon, just epsilon margin for your gradient, if you like. And here, instead of 0, you put epsilon for variational inequalities. Now, here are interesting things. If you have an unbounded feasible set, then approximating weak and strong solutions to variational inequalities is meaningless, for the same reason that approximating optimality gap is meaningless. And let's look at an example just to convince you. So consider the function x times y. It's bilinear, so it is convex concave. And let's take it to be unconstrained setup. Your operator, the way I defined it, would be this, right? And the min-max point for this problem is just 0, 0. Take any point that is not 0, 0. Then your strong solution guarantee, so you would want to bound this by epsilon, by monotonicity is greater than or equal to the weak solution guarantee. And now you unpack what this is. You write, this definition of the operator. You end up with this. You simplify. And now, if you have that either x bar or y bar is not 0, which means you're away from the min-max point, no matter by how little, then because you're taking soup over the real line, you can always push this to plus infinity. So as soon as you move away from this 0, 0 point, what you would like to bound, this guarantee, becomes infinite. So we cannot really talk about approximation here. We need compactness, in other words. But even if you have compact setups, so let's say we have that the diameter of our feasible set is some finite d, then the picture looks like this. Any epsilon approximate weak, well, I should go in a different direction. The set of all epsilon approximate weak VI solutions will contain the set of all epsilon approximate strong VI solutions, which will in turn contain the set of all epsilon over d solutions to approximate monotone inclusion. what I want to say is if I solve monotone inclusion, I have also solved, I get the guarantees for all these other cases for free. And this is the primary reason why I was looking at monotone inclusion, why this setup was interesting for me. And again, this would correspond to finding stationary points. Now, before I tell you how, what the results are and how to get them, let's go over a few just history bits. I may be wrong here, but my understanding is that the MinMax optimization was originally studied within game theory and economics, and some of the first results were about the existence of solutions, and here are a couple of examples. Variational inequalities, they were not originally considered as an abstraction to MinMax. They come from equilibrium problems in dynamical systems. And the whole area was initiated by something known as the Signorini problem. So this was studied since 1960s, and I think Stampacchia was actually the person who coined the term variational inequalities. But it didn't take people long to figure out that there was a connection. Now, in terms of algorithms, some of the results I at least know about were the ones about asymptotic convergence of the iterates, and their results due to Korpelevich, Rockefeller, Popov, and others. But there were also results for non-asymptotic convergence where you can get rate guarantees. There were already back in the 70s, there were results for about linear convergence for structured bilinear problems and for strongly monotone and Lipschitz problems. For weak solutions, in terms of rates, we started getting results a bit later. There were results by Nemirovsky, Nestrov, and others, and also recently there was a number of papers in the ML community that give, let's say, more easily digestible proofs of some of these results, and also have like some new perspectives on these problems. And this includes also results of some of the people who are here on the call. When it comes to strong solutions, there was not that much. I knew about 2 papers, and they were giving suboptimal bounds in terms of the rates they were getting. And then for structured non-monotone settings, those are mainly more recent results. And they need to impose some type of structure because the problem is otherwise intractable, as I mentioned earlier. Okay, so going back to...
We have a couple of questions before we go back to the math.
Okay.
There's a question in the chat by Ryan. And you were talking about, in the previous slide, there was a discussion on all of the notions of approximate solutions, right? So Ryan's question in the chat is, what if there is sufficient curvature for the objective of each player? Would the gap objective in that case still be meaningful, even for unbounded problems? Let's say you have strict convexity, or definitely with strong convexity.
Or strong convexity. With some type of a curvature condition, I would think so, because it kind of implicitly imposes compactness. Like you can even focus your attention on a compact, but yeah.
So, and then
I don't see an issue with it immediately, at least, but maybe I'm missing something, and if someone has something to add, then happy to have a discussion.
It sounds plausible. And then there's a question by Simon, who raised his hand.
Yeah, but I think the approximate, to answer the Ryan question, the approximate variational inequality would still not make sense in even if you strive strong curvature, because of this. You can take U as arbitrarily small, so as soon as you have epsilon, you can rescale things to get arbitrarily big in some sense.
I see.
But that's different than the gap, I think. But so my question was on this approximate hierarchy that you gave, this was in the context of monotone variational inequality, or this was more wrong? It is?
Yeah,
okay.
This whole story is about monotone.
Great. So then what would be an example of a point which is epsilon approximate to either weak or strong variational inequality, but not monotone inclusion? Because you have bigger sets in your thing. So I'm trying to see, like, what's the issue? The issue is perhaps just the scaling. If you just increase epsilon big enough, it's fine. Or is there really something that makes things different? Because for epsilon equals 0, you said they're all the same, right? So I'm trying to understand.
For epsilon equals 0, they are all the same. Well, I mean, one example that comes just from the top of my mind is just going back to okay, so this is for constrained compact setups, but for the unconstrained setup, we saw that if I moved a little bit, I would make the gap infinite. So I think with this I could make the scaling, just make the feasible set really large. And get to, but then, this would scale with D. Let me see. I haven't thought about that, so I don't have an example that comes like just straight from my mind.
Okay, no problem. We can take it offline for later. But basically, one question for me is just that perhaps the scaling is different, and that's why they're excluded, or the nature of the solution is different, which is a bit. Would be
so I find it kind of easier. It's harder for me to think of, well, I guess you can do a mapping, I guess, from convex optimization to a min-max optimization with a similar idea. So let's do this. So consider a convex function. You can have a small optimality gap, but have a really large gradient, and vice versa, right? What this would correspond to is monotone inclusion is roughly having a small gradient, and these two are having the small optimality gap. So you can have a very small gradient at a point that is really, really far from your optimal solution. And that would make your optimality gap large, even though the gradient is small. Do you have the picture in mind?
That's good. That's helpful. Thanks.
Okay, good.
And one last small question from me. I'm sorry to prolong the interaction here, but can you give us a little bit more insight on the difference between weak and strong approximate VI solutions? Because it seems that's an important part where you draw a line between literature.
Yeah, so let's go back to the definition. The strong solutions, as far as I know, were the first ones that were being considered. In a sense, these weak solutions are like a relaxation, because weak solution guarantee implies a strong solution guarantee. Now, if you think about this being a gradient, strong solution is something that you directly map to the optimality gap. For a weak solution, you need a little bit more. And in terms of the algorithms, normally when we work with weak solutions, we end up only getting guarantees for an average iterate. For strong solutions, we normally get guarantees for either the last iterate or the best iterate, but like individual iterate.
I see. Okay, I'll keep an eye out for that. Thank you.
Yeah, I'm sorry that I don't have something that's more to the point.
Well, it's a technical definition. I think I get it, but yeah, I will let you proceed.
Okay, yeah, thanks for the questions. Okay, so the very basic version of the problem. So in the paper, obviously, you know, that this is written in the formalism of monotone inclusion and for all the different setups. But the basic version of the problem is, let's just focus on the unconstrained setup where we want to find the small norm of the operator, which would be like the small norm of the gradient. And again, so here I'm focusing on convex concave setup where this F is monotone. And as I said at the beginning, this problem is well defined even when approximating the optimality gap is not. In general, what you can say is that if you get an algorithm with an optimal rate for this problem, then you get an algorithm with the optimal rate for the optimality gap, given, you know, when the optimality gap is well defined. How about the opposite direction? I mean, I wouldn't be asking. No, you don't get it in general. And there was a paper at last year's COLT that showed that then, and this is super informal. You know, if you go to the papers, you can get a formal statement of the results. But the bottom line is that some of the algorithms that we have that give optimal rate for reducing the optimality gap. So things like extra gradient, mirror prox, Popov's method, dual extrapolation, you name it, they actually give suboptimal rate for reducing the norm of the operator. The two rates should both be 1/k. These algorithms provably, and actually any algorithm from the same class, cannot get anything faster than 1/√k. Okay. So in other words, this is a more general problem to work with. Now, what is the structure that I'm going to use here? It is a very well-known fact. I'm not sure who to attribute it to, but it is something that is in textbooks. And it tells us that if we have an operator that is co-coercive, then it is in a certain sense equivalent to another operator that is non-expansive, or one Lipschitz. And then we'll see why this is important in a bit. Now, co-coercivity is a very strong assumption. It implies that this operator is monotone and Lipschitz. The opposite direction does not hold in general. So it is stronger than assuming that we have a monotone and Lipschitz operator. However, it turns out that if you understand well this toy setting, then you can get results also for the monotone and Lipschitz setup, and strongly monotone and Lipschitz setup. So you can handle all the interesting classes of problems. Let me just quickly tell you what the results are, and then I'll share few ideas from the paper. So the problem classes I have looked at here are when the operator is co-coercive. So it would satisfy something like this. If it was just monotone, you would have 0 here. But now you have something stronger here. This actually implies also Lipschitzness. You would just do Cauchy-Schwarz on the left-hand side. The second class would be operators that are monotone and L Lipschitz. And the third class would be operators that are L Lipschitz and M coercive or M strongly monotone. Here on the right-hand side, you would have U minus V squared. Compared to co-coercive, looks like a small difference. It's a big difference in the assumption. So here you have F of U minus F of V squared. Here it's U minus V squared. And I'm interested in methods that are parameter-free, meaning that your method should work even when you do not know either L or M. But you are kind of guaranteed that you get a problem from a pre-specified class. Now for the results, there's this huge table that looks at first intimidating, but I'll tell you how to read it. In terms of just notation, D would be the diameter of the set, D0 initial distance to opt, epsilon target error. These are the results from my paper that I'm not showing yet. the other row would be the best known. And there are 3 big columns for the 3 problem classes, and then guarantees that you get weak VI, strong VI, monotone inclusion. So each one of them will have these 3 sub-columns. Green color means that you have a parameter-free method. So you can see prior to this work, we only had that for weak VI solutions for these 2 problem classes. And yeah, red means you need to know the parameters. Okay, so in terms of the iteration complexity, the results I got are as good as the best known ones, but parameter free for all setups. And it's possible to show that this is actually optimal. You cannot do better than this.
Can you explain shortly what parameter free means?
Parameter free means you get the problem from one of these classes. So each class is described by some parameters. So this one is described by L. This one is also described by L. This one is described by L and M. Your algorithm needs to be guaranteed to converge without having access to the value of these parameters.
Thank you.
Mm-hmm. Actually, it shouldn't know any of the parameters. Maybe you can say it knows epsilon just to know when to end, but nothing else.
Sure. Not about the problem class.
Yeah. I mean, typically these D and D0, most algorithms will work without knowing them, so they are not as interesting. But not knowing L or not knowing this M for the strongly monotone, those tend to be a little bit more difficult.
Okay.
So for L Lipschitz and monotone, in the weak VI solution, the result I get is a bit off. So this still is hiding a log 1/epsilon factor. But when you look at strong VI and monotone inclusion guarantees, you actually get an improvement over the best known prior to my work. So the previous results were 1/epsilon squared, and here I get 1/epsilon. And for the Lipschitz and strongly monotone, there is again O tilde. In this case, it is hiding log L/M, so log condition number factor. But all of these are parameter free. Okay.
We have a question from
Yes.
Simon again. Go ahead, Simon.
And so here, when you say a result for weak VI, for example, it means that the approximation guarantee that is measured in the max over U of FU, U star minus U, weak VI, etc., right? Which means that, for example, if you are epsilon approximate for the weak VI, you're epsilon approximate for all the other ones, right? So that's what, because it's the most stringent criterion.
The other way around. If you're epsilon over D approximate for monotone inclusion, then you get weak VI and strong VI. That's the direction. So weak VI approximation does not imply strong VI or monotone inclusion. The other direction holds. So monotone inclusion implies strong VI, which implies weak VI. And actually, that's the way I get these results. I am solving monotone inclusion, so that's how I get all of these other ones.
Well, the part I was confused is because if you look at your approximate criterion box for the weak VI, you say that something is true for all U, so you can just set U equal to U star, and then you get the strong version. Oh no, because you move things around. Okay, sorry, that's my misreading of it. Perfect.
Okay, no. We're good.
So that's why
one more quick.
You said that the standard. That's why you said the standard results were giving weaker guarantees because they were only giving guarantees on the weak VI.
Yeah.
Okay, thanks.
Yeah.
And we have one more question from Sharan.
So you can't do acceleration, so you can't improve the epsilon to square root epsilon?
No, you cannot get square root epsilon in general, and there are lower bounds for that.
And are there also lower bounds that this dependence on D is essential? So can we improve like the D to D naught in like the first few results?
Here, no, we cannot. No.
Okay, and for the strongly monotone case, I guess you can do something like a line search and make it parameter free, right? And get the same rate.
Yes and no. So you can relax the knowledge of L very easily for any of the existing algorithms. To relax the knowledge of M, you can do essentially what would be just run the same algorithm for different guesses of M.
No, but you don't need M for getting these linear rates, right? Like, because it's deterministic, 1 over L type step size is enough. So you just need to approximate L, not M.
I see. So you're saying you can actually get this convergence rate without the knowledge of either L or M?
I think so. I don't know where you need the M, but maybe I'm missing something. But like for convex minimization, we don't need M, right? In the deterministic strongly convex case, we can just set the step size to 1 over
gradient descent, yeah, you do not need. Like if you want suboptimal rates, then yeah, you do not need it.
Yeah, and same for extra gradient. You don't need them there also.
Okay, you may be right. I haven't seen the analysis that would completely drop the knowledge of either parameter.
So in our paper, one of these results is like, we have it in like the stochastic setting, but we do like some kind of line search to get rid of the knowledge of L, and you don't need M, I guess, and you get the same result, I think. Yeah, that's right.
Okay, good. Yeah, please send me the link after the talk and I'll update this. Thank you.
Yeah, thank you, Sharon. Okay, thank you, Jelena. Please proceed.
Okay, so let's see how to get this. So the basic algorithm that I was interested in here is known as Halperin iteration. It's a classical algorithm from 1967, and it is used for solving fixed point equations for non-expansive maps. So fixed point equation is things like this, where this T is an operator. It maps a vector from RD to a vector in RD. And non-expansive means that the distances do not expand. So it is not necessarily contractive, that this could be satisfied with equality. These lambda Ks, I didn't write it on the slides, they're step sizes. And the results I'm quoting here would take lambda Ks to be of the order 1 over K. So what you're doing is you're mixing in a little bit of your initial point, and the rest is just the map of the previous point. Now, in terms of convergence, there was a recent result by Leader that even gets this nice constant here, and it shows that if you're applying this Halperin iteration, you converge at rate 1 over K. He used this performance estimation framework, which looks at the worst case performance of algorithms. It is a semi-definite programming-based framework, very, very powerful, but you do not always get intuitive analysis because you numerically kind of figure out how to combine different equations to get the analysis. Now, going back to this simple fact that tells us that there is a certain equivalence between non-expansive and co-coercive operators, you could simply say, okay, if I take this to be my map T, so this being non-expansive, well, F being co-coercive implies that this thing is non-expansive, and let's look at the fixed point of T. So what is the fixed point of T? Well, I mean, it is exactly the 0 of F, which is what we're looking for. And even more, like if you look at this type of guarantee, that this is the same as making the norm of F small. So you get for free already from this result something that converges at rate 1 over K, which turns out to be as good as possible, but you would need to know L to apply it, which is this co-coercivity parameter.
We have a question by Gauthier. Go ahead, Gauthier. Let's try to keep the question short.
I'm gonna keep it very short. Very nice slide, by the way. So this algorithm, the Halperin iteration, so it reminds me things that are called anchoring. I don't know if you're aware of like anchoring and how is it related to anchoring.
I have seen people use the term anchoring. I am not sure if there is any difference, because the papers in which I have seen them, they were effectively using some variant of Halperin iteration. Now, what anchoring here does, it gets one very interesting thing that I'll show you like towards the end of this part. Let's keep it as a surprise for a while.
Amazing, thanks.
Yeah, no problem. Okay, so this is the algorithm that we want to apply, but without knowing L, right? So this is my operator T. Okay, so what I did here is I came up with a different analysis for this algorithm that uses a potential function that has two parts. One is this norm of the operator, and another one is this inner product term. Here, this would be my guess for the co-coercivity parameter, and this lambda case, just as a reminder, is the step size. So the whole idea in the analysis is to argue that this potential function is non-positive, and that's, you know, where the technical work happens, because if you have that, just by rearranging this whole thing, it gives you this. What you do is add and subtract U star, where U star is the optimal solution. Because it is optimal solution, you can argue that this is non-positive. So you're left with this term. You apply Cauchy-Schwarz. You know, if this was 0, you would have been done anyway. So let's say it's not 0. You cancel this f of uk, and this is what you end up with. And now, as long as, you know, what you're doing does not overestimate L by too much, and the whole analysis works for the standard step sizes, you are done. And, you know, you show that it does. So the iteration complexity is of the order 1/epsilon. Now, there are ways to extend this to other setups, but because this is taking a little bit longer than I thought, I would skip those parts and instead just try to tell you a little bit about other results as well. So let me just, in case you're interested, just tell you how you extend it to other setups. So for constraint setups, you would use something similar to gradient mapping in convex optimization. For setups with monotone Lipschitz operators, you would use, you will need to extend the analysis to work with inexact operator evaluations, and the map you would be using is the proximal map. I think people are familiar here with that, also known as a resolvent. And for the strongly monotone Lipschitz operators, you use adaptive restart. You just use the algorithm for this part, and you restart every time you have the current T. And to certify near optimality of the results, there are known lower bounds by Ouyang and Su that are for MinMax optimization. And there is a way to kind of reduce all of these problem classes to each other. So you can deduce lower bounds for all of these problems from their lower bounds. Now, going back to the anchoring question.
So, Jelena, before you go to a new section, we have a question by Sharan. And yes, go ahead, Sharan.
I'll keep it short. So in this, looking at the proof, so where do you get the dependence on D? Like I say D naught.
For monotone, so this is for making the operator small.
Yeah.
For monotone inclusion, there is no dependence on D because it is just making the norm of the gradient small. If you were to translate it into weak VI solution, there you would get D.
Oh, I see. Got it. Okay. That is
Think about optimality gap, like less than or equal to inner product of the gradient and distance, and then do Cauchy-Schwarz and take a soup.
Yeah, I got it. Okay, awesome. Thank you.
No. Okay, going back to anchoring and what it gives us, and one reason why I find this Halperin iteration really, really interesting. So all of the results I told you about were actually for Euclidean setup, but this property holds for any norm for Halperin iteration. Halperin iteration converges to a solution that minimizes the distance to the initial point. That's what the anchoring is doing, and why this was considered initially, and then why people are finding it so interesting in the literature on non-expansive maps. So here I have an example of a function that has many solutions. All are within this pink rectangle. So, you know, wherever you initialize, you would be converging to the closest one. Now, if 0 was a feasible solution, this means you would be converging to a solution with the minimum norm. So you get some type of implicit regularization, which I think is super cool because you get it for free. Okay, and mixing this in is very important. If you didn't mix it in, you would be doing essentially gradient descent ascent, and we know that doesn't converge. Okay? Okay, very briefly, because I know I'm already kind of going over time. What happens in non-convex, non-concave setup? So same problem, just let's assume now we do not have a monotone operator. If you were working directly with F and only assuming it is Lipschitz, then the hardness of the problem, so if you were not you know, looking at how it maps back to a function and the MinMax problem, you're just looking at the Lipschitz operator, the hardness follows from classical results from late 80s, early 90s, because the problem becomes equivalent to finding a fixed point of a Lipschitz operator. Now, for to say that the MinMax problem is hard, you need to be able to map this hard instance to an actual MinMax problem. And that's more or less what is done with lots of technical work in this recent paper. Here, they need compactness of the feasible set to guarantee existence of this epsilon stationary point. But it is inspired by the construction from these classical results. So if I'm being super precise, we do not have lower bounds for unconstrained, non-convex, non-concave MinMax. But given these two results, I would not hold my breath. There's no reason to believe it would be easier. Okay, now note that here, all I care about is just finding a point with the small gradient. And when you look at first at this problem, you know, especially if you're used to working with non-convex optimization, in non-convex optimization, if a function is bounded below, you know you'll find a point with a small gradient by doing gradient descent. Or if it is bounded above, you could do gradient ascent and get a small gradient. So what's the deal? Well, you know, your baby problem, which is convex concave, is not bounded either below or above. So you cannot be making this assumption in the unconstrained setup. Of course, you could be making this assumption in the constrained setup, but then the discussion becomes a little more complicated because you need to care about the sign and other things, and I don't want to get into that discussion. But it is kind of tricky, yeah.
Can you equivalently say that the gap, this duality gap, is bounded below?
So let me see what you're trying to say. So if you assumed that the duality gap is bounded, would you then be able to argue about convergence to a stationary point?
Yeah, you're trying to minimize this gap, and you know it's bounded below, right?
You would want it to be bounded above if you're talking about the gap, but or below. But, I would say above, but anyway, the gap is always bounded below by 0, right? So I think that would potentially be a reasonable thing to assume, but I don't think it would help you. because in the constrained setup, in the compact setup, it is bounded, but still we have hardness results.
Mm-hmm.
And I wouldn't know, in the unconstrained setup, I would not know how to use that algorithmically.
I see.
It seems intuitive. It seems like a natural condition, but I actually would tend to think that it still doesn't help.
Indeed. The hardness results are there to remind you that it's a hard problem. Okay.
Yeah.
Thank you.
Okay, so what is the structure here that I'm talking about? So what we did in this work, we introduced a type of a condition where, so if you had a 0 here, that would mean that a weak solution exists, or MVI solution exists. So this relaxes that. Now, let me just tell you what are some special cases and why this class makes sense, in my opinion, at least. When it equals 0, you get the existence of MVI solutions, and this is something that was considered in the existing literature, and it contains all the nice extensions of convex-concave setups. I don't know why I wrote bilinear here, but it contains like these extensions of convex-concave. It also gives as a special case something that is known as co-hypomonotonicity or co-monotonicity. It was considered in early 2000s, a condition like this, to explain why proximal point algorithm was converging even on non-convex, non-concave problems. That's how people came up with it. And this you can see is a generalization, because if I put v equals to u star, then f of u star would be 0. There are also some examples of structured problems in reinforcement learning. So there is this von Neumann ratio game that was in this recent paper, where this just kind of, let's say, gives you a condition that explains why some type of extra gradient method would converge that you would not be able to explain by these special cases. So let me just state the result. So the algorithm we consider is very similar to extra gradient, just take a little bit different step. So extra gradient would normally take the same step size in these two. And you get something that converges with rate 1 over epsilon squared. And it's possible to also extend it and get convergence guarantees for stochastic setups. But it becomes 1 over epsilon to the 4th, and I don't know how to get anything better than this, even with other algorithms. And now, if I can have just a few more minutes, I would like to mention one last result, just to end kind of on a positive note, where MinMax perspective can be useful. And this is joint work with my postdoc Xiaobing Song and my colleague Steve Wright. It's to appear in ICML. So these finite sum problems, many of you have worked on. They're very frequently considered in machine learning, normally motivated by empirical risk minimization, and they're very well studied, especially in recent literature. We have tight complexity bounds for all standard problem classes that we get by making assumptions on F. And just to remind you what these are, these are like for Lipschitz, non-smooth problems and smooth problems. The results I'll talk about are for this row for non-smooth functions, although I have some ongoing work that will also handle this part. But what I want you to pay attention to is normally we try to get this part of the bound. And here it is necessary to have root n. So n is the number of data points, number of finite sum terms. Okay, just remember that for a second. Now, when we look at common ERM problems, they all have this structure. You have loss plus a regularizer. And yes, you can write them in the finite sum form, but these finite sum terms are not arbitrary. You don't get any dependence on x. You actually get for many common loss functions, this separability where your Li only depends on the data row AI. Now, the reason this is useful is if you use the definition of a convex conjugate and write this in a MinMax form, then here you get a function that maps R to R. It's a one-dimensional function. And 1D functions are really nice. They're really nice to work with because one-dimensional problems are also easy to solve. And so further, what would be the case is that because this is a one-dimensional function, I can always find its proximal operator easily. Like, it's a problem I can solve to high accuracy with whatever I want, like with interior point method if I wish, but I can just do even some type of bisection search. For regularizers, prox operators are normally easily computable because we tend to do things like lasso or elastic net regression or whatever you want. So in particular, the examples that would satisfy this would be, you know, support vector machines, least absolute deviation, lasso region, and so on. Now, when you take this structure into account, here are the things you can get. If this convex conjugate of the loss and the regularizer are just convex, they could be non-smooth, but we can compute prox operators. This is what you get. So there is n log n, and the constant here is really 1. I could even take it in front of O. And then what you pay is the maximum row sum, row norm of the data matrix over epsilon. If your regularizer is strongly convex, so if you were doing, let's say, elastic net, and then you can reduce it to root epsilon. But what is interesting here is that there is no dependence on n. In particular, you shave off this square root dependence on n. And what we show is that you can get this with the iteration requiring order dimension amount of work. So this turns out to be quite efficient. And in particular, because we are taking into account this special structure, this separability, we managed to shave off this root n factor here. Do I have 2 more minutes just to say a few words about the algorithm, or I'm fine?
Yes, you do. You can take another up to 10 minutes if you want, but you know, we want to save a little bit of time in the end for discussion potentially.
Okay, I will need just a few minutes. So what is the algorithm? We start first with the full gradient algorithm that does not assume any finite sum structure, that just has this bilinear term and 2 functions. And we call it primal dual accelerated dual averaging. It can be seen as a dual averaging counterpart to the primal dual method of Chambol and Pock. So there are 3 steps, similar as in Chambol-Pock. So you have the extrapolation step, dual step, and primal step. These things here are the estimate sequences. I won't write what they are. Let me just say that this extrapolation step is really important because it is essentially what allows you to do these sequential updates of primal and dual. And really that idea is from Chambol and Pock. So the algorithm that we get now for when we have this finite sum structure is a variance reduced variant of this algorithm. What you would do is at initialization, you would do 1 full step with full gradient. This is important for the analysis. I can't tell that it is important in practice, but it is what we need to cancel out the error. So you know, it requires 1 full pass through the data. Then in the main loop, you do the same extrapolation step as before. You do a coordinate step on the dual side and the full gradient step on the primal side. And it is possible to show, of course, with lots of technical work, that you can implement this with per iteration complexity order D. Here are some numerical experiments. So compared to the stochastic version of Chambol-Pock, which is this SPDHE, stochastic primal dual hybrid gradient, it doesn't look that much better. So the red one is our algorithm, the orange one is SPDHE. I tend to believe that you can prove similar results for SPDHG, but we didn't have them before, and this is sort of the first theoretical result that shaves off this root n. But it's not worse. It still works pretty well. Okay, so I'm at my summary slides. Min-max optimization can be deceptively similar to standard optimization, but there are some special things we need to really be careful about because problems can be much harder than they appear. Sometimes we cannot do things without any structure, like in non-convex, non-concave setups, but sometimes structure is just plain useful for getting faster results. I have listed a few open questions and problems here. I don't need to read through them. I can discuss them if there are questions. So I'll stop here to just open the space for a discussion. And thank you all for listening.
Thank you.
Mm-hmm. Mm-hmm.